let's have a look at another find a Thevenin equivalent circuit question. In this case it says use Thevenin's theorem to find V0 in the network below. Again, it's not a great question. What does it mean? Well, let's instead say find the Thevenin equivalent to the left of the terminal of the circle to the left of the terminals AB. So I want to replace all of that by its Thevenin equivalent, and then if I do, I'll put the Thevenin equivalent there instead of all that stuff, and I'll end up with quite a simple circuit, and I can find V0. But it's a bit ambiguous as it's first written. Let's do that one. Circuit to the left of AB. What do we notice? Well, there is a dependent source. It's a current dependent voltage source in the circuit. There's also an independent source. One thing you need to be careful about, whatever the controlling variable is, it has to be inside the box. So here, it depends on Ix. This branch here has to be inside. Okay, we couldn't have that outside and find the Thevenin equivalent of what was inside. That wouldn't make sense. Okay, so the controlling variables need to be inside the box, and we're finding the Thevenin equivalent of all of it. So that means the 2K resistor has to be included when we're finding our Thevenin equivalent. So I want to get rid of that. Find the Thevenin equivalent of that circuit. First, find the open circuit voltage. So you find VOC, the voltage between terminals A and B. That's your Melt's question. So see if you can find VOC. At this point, nothing to do with Thevenin as such. Circuit analysis, find a voltage in a circuit. You can use mesh analysis, loop analysis, or nodal analysis, or perhaps mesh analysis would be, there are just two meshes there. Find the mesh currents and then you can find VOC in reasonably straightforward fashion. So yeah, feel free to chat, get on with it. It's a little bit of work, certainly not 10 seconds, probably a few minutes. Thoughts?
Just voltage or maybe.
So you got, yeah, so what have you got that there for?
Yeah, no.
You're going to get rid of it?
Yeah.
Okay. All right. Yeah. So you could put your two mesh currents in, loop analysis. You could say, well, yeah, there are just two loops, currents I1, I2 in them. KVL around the two. Any thoughts? Tired? So am I, mate. I have to bloody lecture. Stay awake.
Out of respect for you, sure.
Yeah, thank you very much.
How's it feel?
You probably stayed up till 5 in the morning.
Obviously.
You did?
Actually, no, I woke up at 7. That's all. And that was ready.
That's early, is it?
Early for me.
Public transport. Yeah. It's that walk. Everyone else can just catch the train. We have to walk.
Actually, no, I think
10
it's
minutes
the
to
bus
get
that goes all the way around.
Yeah, no, we can just walk down, catch a bus, go
You can.
You can catch a bus to the bus.
Which college? You're all in the same one? Is that the best one? What's it known for?
Huh?
What's it known for? Do you play sport against each other?
Yeah, we play soccer on Tuesday against everyone else. I think we're either first or second on that.
Yeah, no, I should come back more often. See ya. Sorry, mate. I am sorry. Go back to sleep. It's all recorded for posterity too. But you didn't give your name, so that's all right. All right, let's see how we're going. Well, so only about 36. I'll count to 10. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Well, I can say only 18 out of 61 got the correct answer, which is minus 6 volts. So given that only 18 out of 60 got that, I think I better have a little bit of a look at this. You could use nodal, you could identify that, etc. I'm going to use, I think in the notes, in the things I put online, I use nodal analysis, but I'll use mesh, say now, in the lecture. So you can have a look at it two different ways. Call that I1 and I2. Two meshes. I need two equations. If I start up here and go clockwise, I have 1k I1. So that's through there. Plus 2k I1 minus I2. So now I've gone through there. Plus 2,000, should have written 2k, Ix prime equals 0. But Ix prime equals what? I2. It's this current over here coming down through there. That is my loop, my mesh current I2. Therefore, 3k I1 minus 2k I2 plus 2k I2, substituting this into there, equals 0. Therefore, I1 equals 0. The I2's cancel, minus 2k I2 plus 2k I2. I get left with I1 equals 0. So one of the mesh currents is 0. So now I just have to go to the right mesh. Is there any problems with that? So I know you could all have done it. Maybe you thought, oh, there's got to be something wrong. There doesn't have to be anything wrong. That's, in this case, I1 would be 0.
But is it possible that the current can be 0 in the loop?
That's absolutely possible the current can be 0, yep. There's no current source of 2 milliamps or something. So Just because there's a dependent voltage source there or a voltage source doesn't mean you can't have zero current. You can have any current through a voltage source depending on the rest of the circuit. In this case, the rest of the circuit is such that there'll be zero, I1 will be zero, and there'll be zero current flowing through the dependent source. It just balances in such a way that there's no current. I don't really need to put this I1 in anymore, but for completeness, let's do the right mesh. So around this one, in that direction, I can write 12. I've done the 12 volt source, plus 2k I2, plus 2k I2 minus I1 equals 0. That I1 was 0. I just worked that out. Therefore, 12 plus 4k I2 equals 0. Therefore, I2 equals minus 3 milliamps. So loop current I2 is minus 3 milliamps, and I1 is 0. Is that okay? So if you knew that, what is VOC? VOC is I2 by 2k ohms. Mesh current I2 times 2, the current through the 2k resistor, times the resistance itself. But that equals minus 3 milliamps by 2k, which equals minus 6 volts. So VOC is minus 6 volts. A lot of people had 6. I don't know where 6 came from, whether there was just a simple sign that you got wrong or switched, or you just guessed 6 because it looked right. I'm not sure. Hopefully you can see where you went wrong after I've worked through it there. So that's just VOC. Let's quieten down. I'm happy to take questions, but otherwise be quiet. Now we've got to find this short circuit current. The next stage, we short circuit the terminals and look at how much current flows down through those terminals from A to B. That's the short circuit current that we have to find. The next melts I will set up. Should be maybe a quick one. I'm not sure. What is IX double prime? So that's a melts question. What is this current here? Done the IX. Do it.
What's the parallel?
2K is in parallel with 0. Does that make sense? All right. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, so I'm a bit surprised. 31 out of 64 who replied got the right answer, which is 0. What's this voltage? What's that voltage? 0. There's a piece of wire between the terminals. It's a short circuit. You can't have any voltage across it. 0 resistance. So there can't be any current flowing through that 2K resistor. It's 0. So that was... Right, I don't know what people did, but if I combine a parallel combination of 0 and anything is going to be 0, all the current will always just flow through the short circuit and none will flow through the 2K ohm resistor. If any current flowed through the 2K ohm resistor, there'd have to be a voltage across the terminals, but they're shorted. How could there be? So this IX double dash is 0. So we first note that IX double prime is 0. If there are any questions, happy to take them. But it effectively means we can get rid of that and we can get rid of this, because that will be our dependent voltage source of value 0 volts, short circuit again. So now the circuit looks, reasonably simple. I'll redraw it so it's a little clearer. We short circuit down there. That's my 1K ohm resistor. That's my 2K resistor. And I want to know what ISC is. The 1K and the 2K resistor are what? Parallel. They have the same voltage across them. They go between this node and this node. So they're in parallel. If I gave you I've got a 12 volt source pushing through a parallel resistance of 1K and 2K, and I just want to know what the current is. So I short circuit. The only thing is the signs are the wrong way around. In a sense, I need a negative minus 12 volts on 1K in parallel with 2K. So that's how much current will be drawn from the battery. That's I short circuit in this case. That is minus 12 volts on, I didn't put ohms down the bottom, so I won't put volts up the top. 1K in parallel with 2 is the product on the sum, which is 2/3 of a K. So that's minus 18 milliamps. So the open circuit voltage was minus 6 volts. The short circuit current is minus 18 milliamps. So what's the Thevenin resistance? Well, it's the ratio of the open circuit voltage to the short circuit current, which is minus 6 volts on minus 18 milliamps, which equals 1/3 of a KO. The Thevenin voltage is the open circuit voltage at minus 6. The Thevenin resistance is this ratio of the open circuit voltage to the short circuit current, which is 1/3. Yep.
Why isn't the current in that 2K0? Why did you put that to 0?
Why didn't I put the current through the through this resistor?
Yeah.
It's not shorted. It's got 12 volts across it. It's not shorted.
But in that case also it has a 12 volt. Why did you?
No, it's got a piece of wire across its terminals in the first case. This hasn't got a straight piece of wire across it in any sense. If I do a KVL, I'll get that the voltage across that resistor is 12 volts. So there'll be current flowing through it. I can't say that back for this one, which is you can't see anymore. It just had this 0. So if I did a loop around there, KVL would tell me that the voltage on the resistor has to be 0. Okay? So they're very different situations. So I can get that. I replace my circuit with its Thevenin equivalent. Notice the sign there. I've flipped the plus and the minus because the Thevenin voltage was minus 6 volts. So I could have left it just to make sure this is not causing confusion. I could have said that's minus 6 volts like that, but it's the same as writing it like that, flipping the plus and minus sign and writing 6 volts. So that's all we've done there. Thevenin resistance there, and you can then work out V0, whichever way you want to do it, voltage divider, except it's going to be a minus 6 times 1K on the total, which is 2 and 1/3 K. 1K plus 1K plus 1/3. 2 1/3 is the total resistance. So how much has dropped across the 1K? 1K divided by 2 1/3 K times minus 6, which is minus 18 on 7 volts. So again, Thevenin reduced it to a single loop circuit, which is relatively easy to analyse. And I want you to keep in mind, as soon as we've said find VOC or find the short circuit current, that's not Thevenin. That's it. It is just circuit analysis. Back to the simple circuit analysis, mesh, nodal, your favourite technique. So keep the separation between the conceptual notion of Thevenin. It requires circuit analysis to find the open circuit voltage, requires circuit analysis to find the short circuit current. But that circuit analysis itself is nothing to do with Thevenin. You know what I mean? Don't confuse the conceptual notion of Thevenin's theorem with the circuit analysis that you have to do. And it's why in last lecture I just got you to do some circuit analysis first before telling you that it had anything to do with Thevenin. This was another entry last year. Picking up how often I do say it. All right, a quick ECSE application. RFID tags. Many of you, I'm sure, will have heard of them. So radio frequency ID is the use of an object, typically referred to as an RFID tag, applied to or incorporated into a product, animal or person for the purpose of identification and tracking using radio waves. Some tags can be read from several metres away and be beyond the line of sight of the reader. So you can see, I don't know if you can, but in every one of these cattle's ears is an RFID tag, a thing with a little chip and an antenna in it, so that when they walk through certain gates, perhaps, it's triggered, and that is a unique ID, so you can track how your cattle are moving around your farm or the cattle yards or whatever. Similarly, in factories, each of the boxes or whatever you have can have an RFID tag on it, and you can monitor it as it passes in and out of factories into certain locations and so on. So it's very good for tracking your inventory and things. That's sort of what they look like. Most tags contain an integrated circuit for storing and processing information, modulating and demodulating an RF signal and other functions. But the main part, the thing that makes it big, is the antenna. So that's all of that there is obviously the antenna. And all of these tracks around are the antennas. What do you think makes that expensive or relatively expensive? The integrated circuit or the processor on it or the chip. So what people also try to do is get rid of the chip and say, can you just basically have an antenna so that it still has an ability to have an ID, an identification? And you can, by carefully designing antennas, each antenna is unique, and just by reading it then, you can pick up the differences. If you do that, you can make them for a cent. You can print them, you just print different antennas, and that's your tag. So get rid of the chip, make chipless RFID, and you can get them so cheap that they can be on every can of baked beans, you name it. When you get them down to fractions of a cent or a cent, they can be put everywhere. We have a big activity in chipless RFID here in the department. There are some exciting applications. If you mix sensing ability with the communications and identification, it's really useful for food security and food safety. So you could, these ones here have temperature threshold monitoring, which can detect whether a food item has become too warm for too long and is no longer safe to eat. So you could be moving your milk around the place, but if you can be constantly monitoring the temperature that is at, if it goes above a certain temperature for long enough, it's locked into the tag. Okay? And so when you read it, you find out, this one's in trouble. It hasn't been safe. So that's going to have, I think, pretty amazing applications for food security. There's a little one that is a bacterial sensing RFID tag, and it can provide a direct measure of contamination of food products. So I think this notion of being confident in the security of the food that you're eating is going to become more important, and RFID might play a very important role in that. If you don't like that application, maybe you like this one. Here's a young gentleman RFID hobbyist, who also surgically implanted RFID tags in his hands. You can see them both there, under the skin, implanted. Why would you do that? Well, how cool is it to be able to open your home door just by putting your hand near it, or opening your computer just by putting your hand near it? And that's indeed some of the applications that this person demonstrated. But if that's not good enough, his girlfriend has matching RFID tags implanted. Forget about jewellery. Why don't you give your partner RFID tags surgically implanted for the next birthday? This stuff is controversial though. People worry about being tracked wherever they go with their mobile phones and so on. Obviously with RFID, maybe your underpants can be tracked and report on your whereabouts. In which case some of us might be in serious trouble. Okay, so RFID tags, keep an eye on it. Norton's theorem. Well, it's basically the same idea as Thevenin, but we've mentioned it before. Any circuit can be replaced with a resistance, still the same one. So we'll still call it RThev. Still this equivalent resistance, the same as in Thevenin, and a current source, which is in fact the short circuit current. So the short circuit current that we've been finding, we can use that as a current source, use the same Thevenin resistance, put them in parallel, and again, you've got an equivalent circuit. So just to keep that clear, I could do VOC and R Thevenin I could do I short circuit and R Thevenin, and they will be equivalent provided we have this relationship VOC equals I short circuit R Thevenin. So that's the relationship between the parameters. And you can see that what would be the open circuit voltage down here. So if I said convert this thing here to its Thevenin equivalent, what would be that open circuit voltage? ISC times R Thevenin. So I've got it written up there, ISC times R Thevenin. If I wanted to short circuit this, what would be the short circuit current? VOC divided by R Thevenin. So you can see those relationships. You can go back and forth between Thevenin and Norton equivalent circuits just using this relationship, and that's actually a useful technique for simplifying circuits. Just like combining resistors in series or parallel is useful, converting between Thevenin and Norton sequentially is another way of simplifying circuit analysis. Simplifying circuits. Do this switch and then all of a sudden two resistors are in parallel and we can combine them. Switch again and you've got two resistors in series. Norton's theorem is not named after that Edward Norton. It's named after that Edward Norton, who was an accomplished Bell Labs engineer and scientist famous for developing the concept of the Norton equivalent circuit. So, if we want to find the Norton equivalent circuit, here assuming the 6K resistor is a load, so in other words, I ignore the 6K resistor and I find the Thevenin equivalent of that, the Norton equivalent of that. Well, I've already found, we found before for that circuit, it was the one we analysed last lecture, we found that VOC was, I think, 9 volts, that I short circuit was 3 milliamps, and therefore R Thev was VOC on ISC was 3 k ohms. So therefore the Norton equivalent circuit is 3 milliamps and 3 k ohms. The other one was 9 volts in series with 3. In this case, it's 3 milliamps in parallel with 3. I could put my other resistor on it, the 6K resistor back on. And now if you had to find V0, the voltage across the 6K ohm resistor, well, this current flows here, pushes through a parallel combination of 3K and 6K. So V0 must be 3 milliamps times the equivalent resistor seen by the current source, which is 3K in parallel with 6K. What's 3K in parallel with 6K? 2K, so that's 6 volts. And that's what we got at the end of the last lecture as well. Thankfully, it should be the same. So really, if you can find the Thevenin, you can find the Norton. That's the lesson in that. Just remember the two different structures, but if you can find the Thevenin, you've basically immediately also got the Norton equivalent circuit. All right, now there's trouble. What if there is a dependent source, but there are no independent sources? What are you going to do? Well, you're going to answer it on melts. How do you find the R Thevenin in this case? What would you do? How would you find R Thevenin? Dependent sources there. No independent sources though. Right, think about what the VI line would look like, and therefore, how do we find the slope of that line? That's effectively what we've got to do to find the equivalent resistance. What does equivalent resistance mean? All right, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So 10 out of 65 said you can't, there's no equivalent circuit. 18 out of 65 said it's 0. 15 said you zero the dependent source and find the equivalent resistance. And 22 said you apply a test voltage at the terminals and calculate the resulting current. I'll show you what the VI relationship would look like in this case. Remember, this is if I did this. Put some stuff there, measured the V and the I and plotted it. We know it's a straight line, and this time it'll go through the origin. Just like the case when you only had resistors, it'll go through the origin. What you'll find is VOC will equal 0, ISC equals 0. You try to take the ratio, you're stuffed. Okay? Because they collapse to the same point. So that doesn't work. You can't zero a dependent source. We've discussed that before as well. When we did superposition, you always had to leave them in there. You can't zero it. So I can't zero it. I can't get rid of it and just look in and find the equivalence of just the resistors. I can't find VOC and ISC and take their ratio. None of those things work. But what can I do? Put some other voltage on there. Why not make this plus minus 1 volt and measure the current that flows. So that's going up here to 1 volt, going across, working out what the test current is, IT, and what will be the equivalent resistance. Minus 1 on IT. It's just the slope. Yep.
Does the graph have to have a negative slope, or is that just for the session?
So it's a good question. Could you have the way I've got it? What you're saying is, could I have negative resistance? Effectively, that's what you're asking, okay? Because look at the way, yeah? But I'm not going to say you can't. With dependent sources, some weird stuff can happen, okay? But mostly you'd expect it to be having a slope like this because of the way I've defined V and I. I think there was another question. Same question. So you just test it. You just put 1 volt on there and measure the current. Basically, the ratio is going to tell you what the equivalent resistance is. That's almost the first point that we got to. If you only had resistors, it would be one way. You didn't know what was inside the box. How would you find the resistance? Well, you put 1 volt voltage source on there and see how much current flowed. And that tells you the equivalent resistance. So in this situation, dependent sources but no independent sources, that's what you have to do. Apply a test voltage, calculate the current, and the ratio will tell you the equivalent resistance. So that's about as tricky as it gets. You've covered all possible cases. So now you can have a good weekend knowing, Thevenin and Norton.